Let's move on to Chapter 5, Logistic Regression, PCA, LDA, and ICA. By now, you have exposure to linear regression, nonlinear regression, and then how optimization and algorithms can be applied in those two data mining algorithms. Right, a natural extension would be logistic regression, and then on top of that, we're going to discuss PCA, which stands for Principal Component Analysis. If you ever get a chance and have exposure to it, if not, we're going to discuss that. And LDA and ICA, when it comes along, I'll explain what exactly all this PCA, LDA, and ICA stand for. But before that, let's start with logistic regression. So what is logistic regression? Remember that in linear regression, we have a linear function. We have independent variables, multiple independent variables to predict your y variable, right? And then if y is continuous in all the data, then we know we can use regression. It's either linear regression or logistic, or it's either linear regression or nonlinear regression, or weighted least squares, or you do some sort of transformation to make it to be a linear regression. But now, what if yi is discrete or simply is binary? You only can predict either 0 or 1 type of binary dependent variables. Then it becomes a classification problem. And then, I want you to pay attention to some of this word here, like classification problem. Classification is different from clustering. Classification essentially has a label on the data, meaning you know the dependent variable label for specific data set. And apparently it's one class of machine learning problem, classification problem. And then if y is discrete or binary, has multiple categorical values for y variable, then we can leverage logistic regression. So the regular regression model becomes logistic regression when the dependent variable is categorical. In other words, multiple classes, or it's discrete. In a very special case, it's binary. Only take yes or no, or 0 or 1. For example, if you want to predict the purchase behavior of someone looking at something on Amazon, then at the end of the day, Amazon gets the data. This particular customer clicked XYZ and stayed X minutes on X, and certain minutes on Y, and certain minutes on Z, and then after Z, he did go back to X again, things in that nature. And then at the end of the day, you'll see that, oh, he purchased X, or he didn't purchase X. Then it's going to be a value of 1 or 0, or yes or no. Then you want to predict whether a particular customer or whether customers would purchase certain product by doing certain some sort of behavior, some sort of browsing or viewing history of the web page. So that's logistic regression. Okay, so we can use logistic function, also called sigma function, to define logistic regression. So let's use Sx, stand for sigma function of x. It is 1 over 1 plus e powered by negative x. If we use e powered by x to be multiplied on denominator and numerator, we come back with what's on the right-hand side, which is ex divided by 1 plus e powered by x. If we define the time function being ex minus x, this is e powered by negative x. If we define the tan x function to be e powered by x minus e powered by negative x on the numerator, and e powered by x plus e powered by negative x on the denominator, then we can rewrite the sx to be a half times 1 plus tan x over 2. So you can see there's some special properties for this function. That is when s is approaching to 1, that is really when x is approaching positive infinity, y is approaching positive 1 or s, because we're using s in this scenario. So let's say again, from x, when x is approaching positive infinity, s is approaching positive 1. When x is approaching negative infinity, s is approaching 0. In addition to that, s can only belong to this area, which is from 0 to 1. It's bounded function between 0 and 1, and then it has this function form, sigma function form. Let's take a look at derivative of sx. Derivative of sx, good news is something becomes sx itself times 1 minus sx. You can do the derivatives here in between, but the conclusion is really that the derivative of a function can be rewritten as a function multiplication, itself function multiplication. It's actually very valuable results that can be leveraged in neural networks or in deep learning. So in order to take the first order derivative, instead of doing some sort of manipulation of real first order derivative, you can use the original function multiplication to come back with the derivative. Okay, let's leave that aside, which we're going to leverage in neural networks and data mining. I mean, neural networks and deep learning. But for now, let's think about this, continue to think about logistic regression. So the logit function is defined as logit p, which is the odds ratio of log p divided by 1 minus p, and it is log with e as the base to be p divided by 1 minus p. So here there's an important step here. That is how do we get there? So let me use some sort of pen, maybe. Hold on. Yeah, let me get something to write on. So now you should be able to see my whiteboard. So as what we just used, right? Sx is e powered by 1 over 1 plus e powered by negative x. Then if we do sx times the numerator, which is becomes so that we have this function form. And then you have right. Now if you take the logarithm on both sides, what you have is negative x equal to log. You have this function form, so that if you continue with this, should be equal to log of sx divided by 1 minus sx. If you look at this form, it's actually identical to what we saw on the slide. Let me go back there. Oh. Yeah, I was actually sharing this. Apparently, didn't quite work. But take a look at what I just wrote on the whiteboard. So we started with this sx equal to 1 divided by 1 plus e powered by negative x. We use this times the new denominator, then we come back with this. And then we use divided by sx on both sides, we come back with this function form. Minus 1 on both sides, and common denominator, and then negative x, take a logarithm on both sides, negative x equal to log of this. Now x is really inverse of that. X is log of s divided by 1 over sx. Okay, that's what I wrote on the whiteboard, but if we go back to the let's go back to the slide. So you're saying my slide. Yeah, no, that's good. Okay, now we're saying that if we define this inverse function of logic function, then we come back with log p is logic p is log p 1 over p. Okay, if we continue, then we know that if this is really an output of the logistic probability. Logistic probability is 1 over 1 plus e powered by a plus bx. If we rewritten this relationship, we use log p over 1 minus p equal to a plus bx, which becomes a linear model in terms of logit of probability of p. Now we define the odds being the p divided by 1 minus p, then we can use odds to calculate p. P would be equal to odds divided by 1 plus odds. So what does this mean? This essentially tells us, I'm trying to get a pen so that, so this essentially says that we can use a plus bx to predict some sort of function or some sort of function of the probability, right? Meaning that, as we said, for the Amazon example, the customer took a look at different product, stayed on different web page for a certain period of time, and then make a decision on whether he buy or not to buy a certain product. That whether buy or not to buy is a probability, right? It's either 1 or 0 in reality, but it's a probability estimation. So we can use that probability being our dependent variable here, p, and then use independent variable of any other information, including how long he stayed on the page, what other pages he took a look, and then especially maybe even what he has purchased previously, what type of products that he purchased previously. All those information would be useful to predict whether he would be buying or not buying a specific product. That is a probability. Okay, so now let's continue, which says the logistic regression is a linear model of log odds versus x. That makes sense. Log odds is log p divided by 1 minus p, which is log odds, and then versus s. One naive way to solve this regression model is to convert it to nonlinear least squares, meaning using each individual observation of whether he purchased or not, minus this probability estimation based on what we discussed here, and then come back with this objective function. And then we can solve A and B, which is a nonlinear least squares that we discussed in last chapter, how to solve this problem, right? However, it's really not work in the true logistic regression sense, meaning if it's a binary variable, it's let's see what would be the true logistic sense. Let's continue with the discussion on the true logistic regression. For a given data set with binary values 0 or 1, missing a 1 here, 0 or 1, the proper binary logistic regression is to maximize the log likelihood function, which is log L, with this function form, which is the corresponding yi observation times log pi plus 1 minus pi times log 1 minus pi. Pi is this probability. This is based on the theory of maximum likelihood probability. Since yi is 1 or 0, the random variable y for generating yi obeys a Bernoulli distribution. Remember, we have Bernoulli distribution for a certain probability, then the chance that yi is going to equal to y is equal to yi is pi times yi, 1 minus pi, this function form. So the joint probability of all different realizations of I would be equal to each individual one of them times each other. Use this pi. Pi is multiplication of each of the function. whose logarithm is given by function 1. As max L is the same as max log L, the binary logistic regression is to fit the data such that log likelihood is maximized. Okay, so true logistic regression sense is really that instead of using that nonlinear least squares, we should be using maximized log likelihood to estimate our P. Now the problem becomes we're trying to maximize this. How can we solve the problem? We can use Newton's method or any optimization techniques to solve this maximized log likelihood function. Now we use an example to take a look. So the example here, I can quickly go through, but for your exercise, you should implement this example so you have a better sense on how it works. We have a set of observations, x being of these values, y being of these values. We can use the following form. Pi equal to 1 over 1 plus exponential a plus b xi. We can start with some initial number a equal to 1 and b equal to 1. Then we have pi equal to use this function form. We have a and b, we have xi, so that we should be able to get P1, P2, P3, P4, etc., etc. Once we get the Pi, then we can use log likelihood to get Li. We use Yi times Pi each one, and 1 minus Yi times 1 minus Pi, so get the first one. And then we can get every single one of them, right? The next step is what is the here should really not be sum, right? We should be looking at multiplication. So this is a typo here. I'll tell the professor to make revision. I mean the textbook writer, Dr. Yang, to make some revision here. So I saw this when I'm teaching here, right? So we should be multiplication of all of this L log likelihood to come back. Not sure if it's really next this number 1, 2, 3, 4, 5, 6. It's a positive number, so it shouldn't be negative this number, right? So this is some sort of mistake we should correct. And then, but the idea is there. So now you have L. And then by modifying A and B by Newton's method, you got a new A, new B, and then you calculate a new log likelihood. It's possible, this numeric number is possible because after we take this multiplication, we also need to do log L. So just remember to do that, right? You get the log L, then that log L. No, we haven't done any log yet here. So we're really talking about L itself. So this L becomes L max is negative 3.91 after 20 iterations. Once we know the best, after 20 iterations, we know it converge. We have our A and B and L corresponding L max, so that we can come back with the best fit logistic regression model, which is the probability is 1 plus this probability. Now, if you give me any X, I would be able to give you a probability of whether a consumer is going to purchase a certain product. That is application for logistic regression. Remember to implement this example in R or Python and reach out if you have any questions on this. Okay, let's continue with logistic regression. Now we only used one independent variable. What if we have multiple independent variables, such as x1, x2, all the way to xn? As I just mentioned, for the customer in the Amazon example, he also bought XYZ previously. That's some information, historical information. That's one independent variable. He went to another web page for 3 minutes. That's other information. Number one, he went to another page. Number two, stayed there for 3 minutes. So those are new variables that you can leverage in your prediction. So if we have more than one, now we use x1 tilde to represent all the variables. Then the probability should be 1 over 1 plus exponential of W0 plus W1, or we use omega 0 plus omega 1, whichever you prefer, times x1 tilde, etc., etc. Here we use x tilde to highlight its variation for different variables. In order to write them compactly, we can define a new variable, x tilde, which is a vector of all the x plus the extra term 1. And then omega is, or w is w0, w1, etc., etc., and this column, this vector. So we know if we use W transpose times X tilde, we can get to this form, this equivalent, so that we can write the original function more compactly to be this function form. And then we can use logic. P is ln P divided by 1 minus P equal to WT times X tilde. That is the logistic regression for multiple independent variables, right? Now, if we have all the data points, how can we leverage the same concept of maximum likelihood? Hold on, I'm actually going back to the textbook to take a look at this summation sign. Okay, so here actually is missing an important step, that is log. Yes, likelihood function is this, but log likelihood, log L, should be summation of log of each one of them. So that, yes, that's right. So that yi log plus, yeah. This is already log I, that's why this should be summation, that makes sense. Okay, so let me go back a little bit. I still need the whiteboard here. Let me share my whiteboard. Okay, hold on. So we use this to define our likelihood function. If we take a log, if you go back to slide 4, you should see this function. Then log L should be equal to log of this pi function. Pi is multiplication of each one of this. So if we continue with this log of this multiplication should be equal to what? Log of each one of them. And then summation, right? Log A times B equal to log A plus log B. So that if we take the log of each one of them and then sum them up, we should be equivalent to what we have here. That's really what's missing on the slide, but now we got it. Sum of this would be equivalent to now again, log A times log B should be equal to sum of log pi powered by yi plus log y minus pi powered by y minus yi. So that, remember this is brackets, right? There's a summation outside here. So now, if you look at this, it becomes sum of yi log pi plus 1 minus yi times log y minus pi, right? So that's our summation of log likelihood. Log likelihood is something that we're trying to maximize. So if you go to slide 5, you would realize we already calculated each individual one of this, and then we use summation. So it's really not a typo. You know, I said it's a typo earlier, but it's really not a typo because we kind of missed this step here. So let me go back to the slide. One second. Okay, so again, this is a log likelihood function. And if we take the maximized log L, we take a log of, this is a likelihood function, and then if we take the log, we come back with a summation. The summation is really on page 5. Each Li can be calculated by this way, and then if you sum them up, you come back with this negative sign. If you go to slide 6, for the multiple independent variables, this y is maximized log L is this summation of this instead of multiplication. Actually, on the textbook, let me go back and let you know exactly where that is. Right, from on page 94, it has this log likelihood, but didn't have derivation from this multiplication to the summation. So which I have just done on the whiteboard. Hopefully that helps you to understand this this process. Okay, now once we have maximized this log likelihood with this certain summation of certain variables, and pi is with this form, then we could leverage what we just know, use any solution procedure that we have to optimize, to solve this optimization problem. Okay, that's multiple independent variable logistic regression. Let's expand a little bit. We only discussed, so far we discussed logistic regression with binary output, and then we discussed more than one independent variable, multiple independent variable binary output. What if instead of binary output in the dependent variable, it has multiple classification with multiple dependent variables? In other words, it can belong to any certain category. We can use examples such as you want to predict type of person, whether he's a high schooler, middle schooler, elementary schooler, or college student. If that dependent variable is in this form, then it becomes multiple classes or multiple labels for your dependent variable. This is something called softmax regression. It's also called multinomial logistic regression. Multinomial is actually more prevalent. It's more prevalent term or name for this variable or for this algorithm or method. So it is trying to come back with a probability estimation using certain observation. And then we're trying to maximize L, which is negative, sum of each individual observation with each categorical categories for the Y variable, and then leverage this indicator function. This indicator function you can see here, we use is the indicator function, and 1 yi equal to k, then it's 1. Otherwise, it's not 1, it's 0. So this is a likelihood function that not only considers multiple independent variables, but also multiple dependent categories. Then you could use gradient-based optimizer to solve this likelihood function. That's softmax regression. Okay, we'll stop here as a first unit for chapter 5 and continue to discuss PCA, LDA, and ICA. Okay, thank you.